Hello everyone, and welcome again to my live stream where I'm coding a GIF decoder, because that's what the internet needs. Over the last 2 weeks we have looked through the binary format of GIF. We found the actual image data. We drew it to the screen and it was very wrong and blew up the CPU. It was extremely processor intensive to actually draw that stuff. So this week, the very first thing I'm going to do is I am going to turn off the part of the code where we do the drawing, because that apparently caused the microphone, the sound to go weird. So let's not do the incredibly expensive drawing of garbage, so the stream doesn't go wrong again. So let's find where we do that. Context.fill star. Okay, so this is all size. So we do the decode and then we draw it. And let's just do that and get rid of it. We do not want to draw any garbage on the screen. So we have here, I already opened this up. You can see what the garbage looked like before. Now if I refresh, there's nothing. Now where did we get to last week? So we pulled out the data in these subblocks, or the image data. Now the subblocks, I believe, can be up to 256 bytes long. So if your image has more than that, more data than that, you get multiple blocks. And so we're going to pull out each block one at a time. We're going to decode some data, and then that will give us what the colors are for the image. And then at the end of the image, I was just throwing an error because I did not want it to do more than one image. I just wanted to, we draw the image and then we just stop. And I'm happy with that for now. Now, when I was getting doing this decode, so we called lzw.decode, this currently does nothing. So that is what we are up to today. Now, unlike previous streams, I've actually done some preparation this week. Madness, I know. And so I've actually been looking at LZW compression, and particularly how it works for GIFs. So if you see me looking over in this direction, that's me looking at my other laptop to see my notes. Hopefully I can do most of this from actually from just looking at the spec. So where do we get to? So one thing that I noticed when looking through my notes is here, we pass through this initial code size. So LZW decoder. When we create one of these, passing through a min code size, which we get as a byte at the beginning of the image data. Turns out that's wrong. This should be min code size plus 1. Not quite sure why. I guess because you never have a zero bit code, so this lets them go one bigger. It's stored in a byte, so this means you could have 256-bit codes, but the spec for GIF says that 12 bits is the maximum. So it still doesn't really make sense to me that they save themselves from using 0 to mean 0 when they don't need a full byte to put in the number of bits in it. I don't know. Who knows what they were thinking 30 years ago when the spec was written. Pretty much 30 years ago, 1987. So we get our initial code size. That tells us how many bits to read for a code at a time. Now the way LZW works is that the decoder has enough information to work out what the output is based on very little information coming in from the file. That's the nature of compression. You can work out all sorts of information about the process that built up the compressed version from very little information in the file, which is pretty clever. And LZW, both ends of the process, compression and decompression, create this thing called a dictionary. And at the beginning, your initial dictionary is just going to be all of the values that you could have for a single color. So let's say your dictionary starts off, and value 0 is going to be black, and value 1 is going to be red, and value 2 is going to be blue, etc. And let's say we start off and we just have 4 colors. Let's make it green. Then there are 2 more items in the dictionary to start off with. The first one is a clear code, which is we'll talk about in a moment. And the next one is end. Now, so clear code is actually, it won't be immediately after the colors if you have a weird number of colors. The clear code comes at the next, I'm going to say round number in binary. So the clear code will come at bits, code 1. It'll come at, yeah. So the clear code will be code 1, 2, 4, 8, 16, 32, etc. Clear code will be a power of 2. And it'll be the next power of 2 after the last item in the initial dictionary. Here, 4 fits perfect. And then when you're reading out the information, let's say the first pixel is black, and then the second pixel is also black. What we do is at this point, we stick a new entry in the dictionary, entry 6, that is going to be black, black. And then we get, say, a blue, and we pick the last part of the previous entry, which was black, black, and we append the first part of this entry, blue. And then let's say the next, and that'll be code 7. And then let's say that we receive a code 7. So that means that we're outputting black, blue, and we create a new item in the dictionary. Code 8 is going to be, and it's going to be the previous thing we got plus the first thing in this set. So this is actually going to be blue, black, if that makes sense. So this blue followed by this black. I hope I'm getting this right. And so on. And so you build it up, and so then when I... so no, that would actually be blue, black, blue. You take the last thing here and all of this. So now code 8, when we get received code 8, that gives us 3 colors in a row, and you can see how this builds up and builds up. And there's one special case to deal with, and that's if the next thing that comes in is code 9, but we haven't assigned code 9 yet. Code 9 isn't anything. What you do then is you put into the dictionary whatever the last thing was, doubled. Oh, sorry, I think it's the... hang on there. Let's go to those notes I told you about. I think it's the last thing in... so we get to a code that we haven't seen before. Last plus the first last. Okay, so so we get the last thing, which was black, blue, plus the first thing, the first item in the sequence that was the last one. Does that make sense? So we start off with the whole array of items that we got before, and then we add on just the first thing in that array. So we create this new code, we assign that to 9, and then we can immediately use it. So this would be like that. Okay. I may have said something slightly wrong in all that. Yeah, when you're creating the new code, when you've got when the last code or the current code mean more than one a list of things, I've probably said something wrong about how we construct the codes that way, but we will see. So I need to just move this around so that I can still see my notes and the chat, because I don't want to. The basic principle makes sense. Oh, cool. That is good to know. Okay. So, window management is not great live stream material, especially when it's on a monitor you can't see. There we go. So, let's get rid of this. So what we're actually getting passed in here. Okay. Code inspection doesn't really work for JavaScript. So when we pass through the data to LZW here, so we're passing the code size, and then we're telling it to decode some data. Oh, that's interesting. So this doesn't actually match. So just passing in data. We also need a length. And we actually need to know the size of the existing dictionary. Do we? No. We don't actually need to know what the values in the dictionary mean. This will just output the list of indexes into the palette. We don't actually need to know what the colors are. Okay. So while we have some data, so for sorry, why am I passing in a length? Why did I think to pass in a length? I should have looked at this code before the stream to try and work out what I was thinking last week. Or even better, I could have watched the video to see what I said about it. So data, what is data? This.parse subblock returns a byte array. It will have a length, so I don't need to pass through the length, right? So up here, oh, yeah, we need to be able to stream in some bits. So I think that's where we got to, is that I was trying to work out what the best way of getting bits out was. So I'm going to create a new one of these buffer readers. And it's going to be based on this array. So my buffer equals a new array buffer. No, it's going to be a new in 8 array of array buffer. If I just use the buffer of array, then I get the whole buffer, and I want a new buffer that only has that part of the array in it. So I create a new uint array from the values and then get the buffer, get the access to the buffer that owns that. And then I need to do something about these lights. I should say, you know, I was running a little late today, so I'm still sort of calming down at the beginning of the stream, because it took me a little longer than normal to get set up here. So I finished plugging in my mouse and keyboard, and then immediately had to come on the stream. So if I seem a little flustered, that's probably it. So we have our array buffer, and I'm going to create a buffer reader. So reader was new. What did I call it? Was it just buffer reader? Buffer reader. Now I can read bits off this. Now this get bits implementation, when so I get a bunch of data from the stream, and it's going to be some bytes. Let's say like this, and let's say that I'm reading off, my initial size is 5 bits. So what I do is I go to the first byte and I chop off the least significant 5 bits, and that becomes my first value. That's the first code that I read off. Then I take this and I'm going to shift it over until it's at the beginning. And then take in, well, okay, it's not what I'm going to do. I'm going to take this and I'm basically going to put it on the end of here and then take 5 bits off the end of here. And that's my second code. So we take whatever we've got left along with the least significant bits of the next byte, and that's how we get our codes. So we take the least significant bits, make it into a code, and then we're going to shift this over to there, and this will get zeros. So these would be our codes from those bytes if we were getting 5-bit codes. And that is what this is doing. So we have some bits remaining from the last time that we did it. So let's say we've removed first 5 bits from a byte. So we have 3 bits that we didn't use. So we keep those as partial, and we remember that there were 3 bits there. Because obviously partial will actually be, when it's JavaScript, it will be a 64-bit double. So we just have to remember how many integer bits we've got. And then we keep shifting the value that we've currently got. So we keep adding on more information at the beginning until our value has enough bits to satisfy the request that we're getting. So if we've got 3 bits of data currently and someone asks us for 12 bits, well, we need to bring in another byte to give us another 8 bits, and that takes up to 11. And then we have to bring in another byte because we're still short, which takes us up to 19. Then we can take 12 bits out, and we're left with 7. Does that make sense? So we're using this bit shift to move the partial over and then put the byte on the front. This is the wrong way around. This puts the bits that we already had in the most significant position and puts the next byte in the least significant position. And we want the other way around. So we'll have to fix that. So we start with partial, and we need to OR it with so let's say we've got 3 bits remaining, then so it's going to be this partial ORed with, and it's going to be this shifted up, oops, by however many bits we've got remaining, so that we don't overwrite any of the information, any of the bits that we've kept from last time. So yeah, and then bits remaining plus equals 8. Yes, that's true. That's still correct. Yeah, presumably the next bit of code is also going to be wrong. Yeah, so basically what we had is, let's say we had these bits remaining, and the next byte comes in like this, 8. What we were doing before is we're saying, okay, shift this over by 8 bits. So we add 8 bits there, and then we OR it with the next thing to get that, to get a more than 8-bit value. But we don't want our bits, current bits that we've got, to be in the most significant position or in the least significant position. So instead, what we're going to do is we're going to take this and move it over, shift it left by bits remaining, which in this case is going to be 3. So we have that. And then OR them like this. So we get this number. So the old bits go in a different position in the number. And we can repeat that process until we've got enough bits to satisfy the request. Okay, so our result is going to be this partial shifted down by this bits remaining minus number of bits we want. So this is still correct, so let's put this back. So this is our final number. We still want to read things off from the least significant end. So we are reading, say, 5 bits. So what we want to do is... no, this is wrong too, because this was also reading off the most significant bits. So what we want to do is say, okay, we only want to return a number which is equal to these 5 bits. So we want to turn all of these ones into zeros, and then have these. And that will be our answer, because obviously, as I say, we can't return only 5 bits. We can return a number with the same value as those 5 bits. So what we do is we take this number and we AND it, with this. So the first 5 bits are 1s and the rest of the bits are zeros. And when you logical AND those together, sorry, no, I do mean, yeah, AND. So 1 and 0 is false because the second one wasn't 1. And this is going to be true for all of these. It doesn't matter what the top one is. This one is 0, so it can't. The AND of these 2 bits can't possibly be 1. So these all end up being 0. And then here, ANDing with 1 will be 1 if the original bit up here was 1, and 0 otherwise, which actually just gives us these bits. Okay, so that's an AND. Yeah, and then once we've done that, we're left with, we then want to take away the 5 bits that we've just returned, so that our bits remaining doesn't have it. And what we do is we shift down by the number of bits we return. So what that does is it would just, every time you shift 1 bit, you basically discard the rightmost bit and put in a 0 at the front, on the left, at the left end, so that you end up with the value of the bits that you didn't use. So the result is the partial we've got, and it's going to be, so how do we make this number of this, basically? Well, this is the same as this, minus 1. And this is a 1 that has been shifted over. 1, 2, 3, stupid tabbing. 1, 2, 3, 4, 5. Yeah, you can sort of see it. if I do that. So we shift it over 1, 2, 3, 4, 5 times, which is the number of bits that we were asking for. Our shift, our mask, is going to be 1 shifted over by number of bits minus 1. So our result is whatever partial value we've got and mask. We have fewer bits remaining, and then we want to take the partial we've got and shift it down by number. So I think we're basically doing it just the opposite way around. So you basically keep padding the end and oring extra bytes until you have either number or greater bits. Yes, exactly. Because so JavaScript can represent any integer up to, I think it's 54 bits. So if we were asked for 55 bits, this wouldn't actually work. And when you do oring and anding and any bit shifting operation, JavaScript actually automatically converts the number into 32 bits. So actually this wouldn't work if you were asking for more than 32 bits. It might not even work if you asked exactly for 32 bits, because we have a value and then shift it, and that might lose us some bits. Luckily, we only need to care about up to 12 bits at a time in a GIF. So this should only, this should never be a problem. But that is the gist of what we're doing. Okay, so we know that our clear code I want to be able to call this multiple times with different arrays. So I guess things like the clear code and the end code need to be, and in fact the dictionary need to be stored on the object itself. So let's do clear code equals, this was 2 to the power of the code size, well in this case it'll be code size minus 1. No, so if we've got 3-bit codes, then the clear code will have 4 bits. So yes, this is going to be 1 shifted over by this code size, and then this end code equals this clear code plus 1. So we're going to have a dictionary. Which in our case is just an array. We don't even need to be an object, because all of the keys will be numeric. And then we need to store what the next is for where we're going to insert the next. I can't even work out what room he is in. I'm in a meeting room just around the corner from my desk. I'm in my office, in fact. And then, so next, this is going to store our pointer to where to write the next value into the dictionary. And that is going to be this.encode plus 1. So we don't need to do that there. That will be initialized when we initialize our decoder. I may have to take out the talk about meeting rooms from the video just because it's irrelevant. Right, so now we can start reading codes. We can just start reading codes. So, what do I do when I run out of data? That's a good question. because I'm going to run out of data after each chunk, each segment, but it won't actually be the end of the GIF. Oh, you know what? Let's make things simple. We don't have to do this super amazingly efficient to start off with. So instead, what I'm going to do, I'm going to push all these blocks, and at the end, I will say that I want to decode. And LZW decode is going to be all of my sub-blocks together. How do I do that with a uint8 array? So, I want to do a join. Typed array. Does typed array have a join? Typed array does have a join. Join with joins all. Oh, that's like an array join. I don't want that. Don't want that. How do I mash a whole bunch together? Because this isn't the interesting problem that we're currently trying to deal with, so image byte, I'm just going to do the dumbest thing that could possibly work. I wouldn't normally use notes, but this bit's complicated, and in the first stream I felt like I was mostly just reading stuff. It was the first thing you ever did with bitwise stuff. So the type of thing we have to start at the deep end. It was the first thing I did with bitwise stuff. That's going to have been a really long time ago. I don't know. I have gone off and looked at all kinds of crazy things in my programming career just for fun. When I was at university, my computer, the installation of Windows that I had on there went wrong, and I ended up only being able to boot into DOS, and I thought, well, you know, what can I do with just DOS? And I thought, well, you know, I could go even lower level, and I started playing with assembly language then, using a DOS text editor and a DOS-based assembler. And so I'm sure I did bit twiddling then. This would have been, 15 years ago. I didn't really know very much about programming then, but I didn't know enough to realize that what I was doing was complicated. Does that make sense? I made a right mess of all that, but that was probably the first time I actually did any bit twiddling. I've done something very similar to this when I wrote a decoder for deflate, which is another compression algorithm that's used in zips and gzips and PNG files. That is a more complicated algorithm, but it similarly reads off just a small number of bits at a time. So the reading the bits part is I'm doing from memory mostly, because I've done this before. I think with PNG it was the other way around. It was with deflate it was taking most significant bits, putting them as most significant bits. Let's see. I wrote a Game Boy emulator last year. That used a lot of bit twiddling, but mostly implementing the instructions. So in your emulator, obviously you emulate the CPU. That has bit shift and or instructions, so I had to implement those. I didn't really use them very much for my own part of the code there. I've used it all over the place. It's one of those things that people don't think you should do in JavaScript. In fact, JSLint has it as an error if you ever use a bit shift operation, which is mad because with typed arrays and things, you're working with actual bytes a lot more now. But I guess if you're still just animating something or changing what the text says on a page, traditional old school JavaScript stuff, it probably is an error to use bit shifting. Where was I? Right, I was going to build up this image bytes, and like I say, let's just do the dumbest thing possible. So I'm just going to create here image bytes, and it's in fact just going to be an array. For const byte of data image bytes byte. And at the end here, we're expecting to pass through. Oh no, this will take any array like. Where's it gone? There we go. So this will take any kind of array like because I pass it to the int array constructor. So that should just work. And then at the end here, I can just pass in image bytes. Let's see what I actually get if I do that, because that might not be correct. Unexpected token. Oh, what have I done wrong? Oh, we have anything here. Oh, let me do that. So our min code size is 8, which, as we know, actually means we're going to read 9-bit codes. So yeah, our clear code is going to be, let's say, clear code 512. So the end code will be 513. Those are 9-bit code. All right, 9 bits can get you up to 511. So that's actually a 10-bit code. Not hugely convinced I've done that right. Let me have a look in the spec here, where it's got has an example. So decompression. For the reading. No, where's decompression? Decompression. Right code. There's a W code size. Establish the code size. To find the number of bits needed to represent the data. Yes, great. Press the data. So establish the code size. Oh no, this is all compression. I want decompression. It doesn't mention it. Doesn't mention it. Okay. We'll see pretty soon if it's wrong. So our dictionary is empty. We should probably fill that, pre-fill it, just to say that code 0 maps to value 0, etc. So we get a bunch of data, and then each of these bytes, each of these 255 bytes, image bytes is getting bigger and bigger and bigger. Cool, that seems like it's probably correct. Image bytes ends up being 125k. So when we do parse subblock, are we correctly throwing away the 0 at the end? I don't know. Should be. So it may be that at the end of each of these subblocks, because each subblock, it starts with a length, and then there's the data, and then there's a 0 to say, hey, this was the this is actually the end. Completely unnecessary, but that is what it does. So let's just have a look at this first subblock, and then look in the data, and do we find, so at the end it does not end with a 0, it does not end with a 0. Size is 255. Okay. And then when we come through, does the next one start with a 0? I guess that's the next test. So parse the next subblock. Data does not begin with a 0. So I just assume that's correct. We'll find out pretty soon. I wonder, something I meant to do, something we should do is test this with a smaller data set. But I'm going to hack out some code, we'll see if it works, and if it doesn't, then we'll see if I need any better test data. This might magically just produce the image of the cat that we were hoping to get. So array is now the full array of data, and we don't have to worry about splitting it up into sections. We just have all of the data for this image. So the last thing we get here should be that encode. That is the last thing that we should get here and should return then. So let code equal reader dot get bits dot code size. So we're going to read some number of bits while code is not equal to this dot end code. Carry on reading. And at the end of here, obviously, we have to do this same thing. And what we'll do is, for now, we will console log the codes and just check that these things look reasonable. For most GIFs, what I would expect to get first is actually the clear code. That's what I've seen in examples, that most of them, the very first thing you get is the clear code. So that should actually give us a nice bit of diagnostic here. So let's find that. So we read a code. The code is 256, which is half the size of what I predicted the clear code to be. And I did say that I expected this to be the clear code. So I think that means that I've made a mistake here. This should be code size -1. No. Well, I mean, this is going to be wrong, but interesting. I'm getting a bunch of codes. Mike hasn't done funny with all the CPU usage, has it? Hope not. I was hoping not to get into anything of it this time. again. Yeah, do let me know if that has stopped, because I can stop the stream and immediately start it again. And oh no, I can't. The stream is all good. Okay, good. Phew. So we've got a whole bunch of data. So I need to put in better watch here. Yeah, there we go. Actually here, so we can actually see what we're getting 1 byte at a time. Oh, right. Okay. So code is 256. We're now thinking that clear code is 256 and end code is 257. So we get a code, 6, end code. Brilliant. Not end code, clear code. Then we come through again, and we get a 0. So whatever color is 0 in the color table, presumably 258. So at this point, after 256, we've got 257 as the end code. We produce a 0, and at that point, because every time we read a code that isn't the clear code or the end code, every time we read another kind of code, we add to the dictionary, we'll have already created 258. No, I'm making a mistake. So if I go back and look at my notes here, we get the code size, and then we get the data size. So that was something that we forgot to do last time, actually. So after reading the code size, the very first thing is actually a data size. Block size. Oh no, okay. You're rambling, Matt. We already dealt with this. This is the block size. This is the size of the block. Our block reading code already deals with this and gives us back the data bytes. So ignore me on that. So no, this is correct. So 256 is our clear code. Read a 0. It's going to add in a 258. Add in a new code, 258. So when we read this 258, it's a. Does it just mean 0? I'm not actually sure. I would have expected that 258 would mean the last two things. We've only had one. So I'm already super confused. Oh, stop it. So this is going well. 259, 260. Oh man, so I'm assuming that the data starts with a run of all of the same pixel, all of the same color, whatever 0 is, so that we get one of them, then two of them, then maybe 3 or 4 of them. I'm not sure. And this will be 5, and then it goes. It should get exponentially bigger, basically after that, until we finally get to a new thing. 269 is going to refer to something we created back here, which is going to be it's going to be all of the same color again. But at this point, 269 is going to refer to a lot of pixels, all in just one code, which is great. What I need is, so I do need some test data. I need some test data. Luckily, I have some test data because I just can't tell from this whether what I'm looking at is correct. So instead of doing this, for now, I'm just going to do decoded equals code test bytes. Could have just copied that one. And in fact, sorry, I'm not doing such a good job of talking in this stream. I am spending too much time thinking, and thinking is bad for streaming. Is that something that can easily be checked in the file? Oh, okay. Message retracted. Never seen that before. Yeah, sorry. Because the lag, I'm not sure exactly what you're talking about. So I'm going to create a new decoder. So I'm going to read all that data. I'm going to stick it somewhere. I'm just going to ignore it. Because I happen to have some test data that has code size of 4. These bytes are 0x8. I'm copying these from my other computer. And I will let you know what this is in 1 sec. C. Oops. So I created a GIF in an image program earlier, and it was just 4 by 4. Oh yeah, I could look at the image and see if the first few bits of the bytes are the same. That is a great idea. Where is my other? This one. That. So let's have a look at the cat GIF. Yeah, so those first few pixels are all, if not the same, extremely similar. And it doesn't matter about any changes between frames because we're currently only reading 1 frame. But yeah, given that there are only 256 colors in the whole GIF, I expect that they did not waste time in having slightly different shades of this same color in that first row. Up to about there, I guess. So that makes sense that you get a lot of the same color. However, I created a different GIF on earlier while I was going through this in my head. And this one, it's a 4 by 4 image, and I can't 100% remember. Oh no, I have it in my notes. So the image was black, yellow, white, and then red, and just red. Thank you. Let's make this a comment so that VS Code won't go nuts at me. And then on the next row, it's just white, 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 so that I have some repetition. And the final row, it's kind of like the first row. All the colours, in fact, no, most colours are different. So this one is blue and this one is green. So I created this image as a test, so that I had a very small image so that I could see exactly what values were coming out. And this is the data for that image. And we can go through exactly how it should decode as we go through. So let's see here what happens. If I go into here, my initial code then is 256, which I know is wrong. I know that's wrong. So I know I have a bug right off. Because my first code should be 8. In fact, my initial code can't be 256. I wonder if this is even reloaded. Have I saved? I haven't saved. Phew, yeah, because you can't get 256 from a 4-bit code. Okay, so initial code is 8. Great. And my next code should be 0, and I do not get 0 at all. I get 298. So I definitely have a bug. And I wonder if that is that's presumably in get bits. So let's decode that, debug that. So when we first come into get bits, our bits remaining is 0. Why is number 9? What is number? Oh, because I'm calling it in the wrong W. Okay. So maybe I don't have a bug in get bits. So the first code is 8. The second code is 0. 4, 5, 2, 5, 14. Perfect. This is exactly what I'm expecting. So get bits seems to be working correctly. Now, so now we can do our first thing in our decoder, our first conditional bit of code in this reader. When we get a code which is equal to the highest possible value that we can represent in the number of bits we've got, then we need to increase the number of bits that we read each time. So if the code equals, and it's going to be this dot code size, 1 over by this dot code size minus 1. So 1 over this dot code shifted by this dot code size is going to be, so if we have 4-bit codes, then that means we're going to shift it over 1, 2, 3, 4. So we end up with a 5-bit number, and then we minus 1, and that shifts this to be that, which is the highest possible 4-bit number. Does that make sense? So if the code is the largest one we can possibly have with this code size, then we increase the code size, and from now on we will read 1 extra bit for every code. So let's go through that again. In fact, since I'm console logging here, I'm just going to do this and have a look. So 8, 0, 4, 5, 2, 5, 4, 5, 2, 5, 14, 15, 14, 1, 11, 3, and then we actually do leave this loop when we reach clear code, which is 9. So this is reading all of the correct codes for the image that I created earlier. But obviously it's not returning the correct values, because some of these codes correspond to an array of multiple values. So let's build that up. So our result is an array, and we also need to maintain a list of past values. So we can call this, let's call this stream. Jake would be happy. So when we read this first code, stream is actually going to be that first code. Oh, and as I said here, the dictionary actually needs filling in. So for 0, that's then -1. Sorry, clear code -1. We want to fill in every value before the clear code. just want to say that list dictionary I equals I. And I'm going to make it an array containing a single value so that we expect that this dictionary actually contains sequences of values, because we're going to have to put those in later. So if we let's make this a method. So we're going to, because we might need to clear the dictionary midstream, let's make that into a method we can call. Because we have to be able to set the dictionary back to what it was initially, which is all of the values up to clear code being set. And I don't think we have to clear anything else. Could be wrong. Like, for example, I don't think we have to reset the code size back down. There's a note at the top of this spec about people doing this wrong. The large code do not handle decompression in this manner. So as we can see, when the decoder's table is full, it must not change the table until clear code is received. Code size is that of the maximum code size. Other than this, it's so it looks like it only clears the table. Clear code. Let's just double check that. Special clear code is defined which resets all compression, decompression parameters and tables to the startup state. Okay. What compression, decompression parameters does that mean? Does this mean the code size? Do we reset the code size to what it was initially? Well, lovely. Another thing we don't quite know. For our the simple test GIF that I've made, clear and end codes aren't in the dictionary. They can never be used to mean actual values. So no, the clear code and end code can never cause more colors, more pixels to be added to the result. The clear code means get rid of the dictionary, and the end code means we're done. So we don't need them to represent anything. I don't technically have to fill in the dictionary for those initial things. I could just have an if condition that said, oh, if the code that I've received is less than the clear code, then actually that's just going to be the original value. But for simplicity's sake, I have not done that. That feels like an optimization that we could do later if we wanted. So if our code equals, I don't know, this dot clear code, then this dot clear. If this dot dictionary code, if it has something, because we're using arrays, then it will be truthy, i.e. an actual array, if we've already set it. So if it's in there, then our result, result equals result.concat. This is a super expensive operation that we're just going to do anyway, so that we can get some working code. Generally speaking, I find working code to be better than good code, at least at the beginning, because once you've got it working, you can then write some tests, make sure it stays working as you go through and optimize. If you start trying to do optimized code, you can get into a place where you never get working code because you can't quite see what your code is doing. So I always want to make sure the code is dead simple and do dumb things at the beginning because it's just easier and you don't know what code you will even keep. After this I could write and realise that I don't need to do it, or that I need to do it in a very different way. So any time I spent optimising it would be wasted because I'm going to delete it. So that's my defense of doing this dumb thing, and it's going to be just whatever this is. This is going to be an array. So I'll take my current result, which is the beginning will be an array of just an array of nothing, in fact, and I will append on whatever whatever I get from the dictionary. Now at some point, so if that's not true, if it's not set, then I need to like these should be. I don't want to do these. I don't want to do anything after these. These mean carry on. Oh no, not that one. This means do nothing else in this loop, because I don't want to do anything else with code. I don't want to do the next bit here. Oh no, I still need to read the code. So, else if. So, either this was a clear code, or it's a code we've already seen, or it's a code we haven't seen. We'll deal with that in a moment. But if it's either of these, and before we do this, we need to add something to the stream. So we have to say stream dot push No, it is different for both of these cases, so we can read it as. So in this case, stream dot start dictionary dot hello. Next code next equals. And this is going to be the last thing in the stream, and then the first part of the last thing in the stream. Does that make sense? So this we're going to add to the stream. We're going to say this.stream.push code. It's a smell. Pulling out the same thing 3 times. Later. So here we're not adding a new thing to the stream. We're going to take the thing from the stream sort of twice. So what we do, it's a thing we haven't seen before. So we take the last thing. So what we're going to add in is this.stream. How do we get the last thing out without actually removing it? This.stream length. Just 1. That's annoying. So last, let's pull this out into a variable. No. I can just hold on to whatever the last thing was. Confusing myself completely. I don't want to set this to be this, especially if the first code is actually the clear code. So how about we just let that be? Here we say current is going to be this. can say last equals current, because that would be true. And put those in. Now we don't need last from here, so this is going to be last.concat last 0. So it's going to be whatever the last thing was, which might be multiple values, plus the first item in that sequence. So if the last thing was just one thing, so let's say the last code we got just encoded to a single white pixel, then what we'd get here is we'd get an array with just white in, with an array with just white, and that would make 2 whites. Brilliant. Whereas if last was like white, red, green, we'd get white, red, green, white. It would be the first thing in the first part of the last result. Bending my brain, too many things that could be current, last, first. Are we talking about codes or arrays of results? It's a little hard to keep in my head what to call things. So here we still need to, so we're adding to the dictionary, but we also need to add to the result. So here we actually want equals this. And then we're going to use it immediately. So it's going to be current, and then this happens exactly the same. The one last thing we need to do here is that we need to add to the dictionary in this case. Because we always add to the dictionary when we don't have clear or encode. So what we add is the last and the current together. So it's going to be last.concat current. Concat is great because you have to call it on something you know to be an array, but if this is an array, then you just get the elements appended together. But if it's not an array, if it's just a single value, it's the same as doing a push, which is super convenient. In this case, I think all of our items should be arrays. If I was doing this in TypeScript, I'd have put type annotations all over the place here, and it would tell me if I was getting this wrong. But what we'll do is we'll step through it in a second and see. Okay. And then here we need to set. We still need to set last equals current here. So I see some duplicated code after all. Yeah, we still need to add this to the stream. Okay. So yeah, we can do that. We can bump this in. So that these things, which are identical between the two code paths, can come afterwards. Looks good. Now let's see what our result looks like. Oh, we have an error. Property concat of undefined. Last is presumably not defined at this point. Yeah, so last will actually, it'll be the first time we come through. So our code is 8. And in this case, that is clear code. So clear down. Fine. Next code is 0. Now, in my test image, 0 is actually black. So our first pixel will be black. It's not the clear code. This.dictionary.code actually exists. So current equals an array, a one element array containing just a 0, meaning black. So you add to this.next is 10, so the 10th thing is going to be last.concat current. Yes, indeed. So last isn't actually set to anything at the moment. And that's actually cool. We don't add anything on the first time around because we don't have two things to stick together. So if it's null, we just set this to null. Should be the only time it can be null is the first time through. Because then we set it here for the next time around. In this case, can we? Is it possible to get an unknown code on the first time through? I don't think so. Oh no, it must be. So if we've got 4-bit codes, it means we can represent a whole bunch of values immediately after the clear code. Now this wouldn't make any sense because last is definitely involved. Yeah, I don't think we can be in this position. So we don't have to do a similar check here. Because the value that we produce is only based on the last value, this just wouldn't work if you've got an unknown code as your first code. Okay. I'm going to put in a little sort of kind of an assert if start next is not equal to the code, throw an error. Because we should only be getting, the only time we should receive an unknown code is for one that we're about to create. So the next code to create should be the same as the code that we're being asked to produce. It's the only time it should happen. If it isn't, it doesn't matter. So we come through, we get our code 8, which causes us to clear. We get our code 0, which is going to be black. Last is null, so we're just not going to do anything. But now last, current is not defined. Last equals current. Oh, you're right. You are right. I only create it in those two, so it needs to be done outside. Oops. There we are. Okay, code 0. Try this again. Code 0 becomes a simple 0. The last thing we got is now 0. So our output stream is now what are we doing? We've got another error. With another error, can we probably push or undefine this dot stream? Oh, not this dot stream. Oh man. Okay, so we push that into our stream, and we fail again. Assign constant variable. Result. Yeah, I created it as a const because I was thinking, oh, we're just manipulating the array. I'm actually overwriting it with a new array, which is the result of this. Cars, I am doing some dirty, horrible, inefficient code. It is simple. Oliver on the stream on the chat says, I guess for this simple example, you'll usually need to check to make sure the dictionary has room. Yeah. Maybe. I mean, that would be like an error correcting thing. It shouldn't ever come to that. Because the encoder shouldn't use any value that is too big for the dictionary, because it creates the same dictionary as it goes along. And the dictionary can grow up to store enough information to have 12 bits, 12-bit indexes. So what's 12 bits? 4096, which less the clear code and end code gives you 4094 possible real codes. So if you try to grow beyond that, you should probably error. So, I should check, I just tried to grow to 13 bits. That's not allowed. I could do that here. So if code size more than 12, but I don't think it's an error. It's just like once you get to this point, just stop growing, and you should never grow beyond 12 bits. I think that's what this means. So at the top of here, there was a warning about people doing it incorrectly. Does not change the table until a clear code is received. The code size is that of the maximum code size. When the decoder's table is full, it must not change the table until the clear code is received. The code size is that of the maximum code size. So that's what I think this is saying. Once we've got up to 12 bits, we never grow, and we just carry on as normal. The only thing that changes is that we don't grow beyond 12. Maybe think about splitting this into different files so that we can see a little bit better. Right. So in theory, this is. I think I've done everything. I think I've done everything that needs to happen. Well, let's see what results we get. So at the end here, let's just see. Unknown code was not next in sequence. Whoops. Code 14. Next is 10. Is it really unknown though? Have we not created code 14 at this point? We should have created code. We're never increasing. We're not increasing next. Okay. So we read in some code, so the same codes that I said were correct last time. That's great. Let's see what the actual result is. What do we get? 16. We get 16 elements. Perfect. It's a 4x4 image. Let me just check this out. So this will be the top row, second row, third row. So 5, 5, 5, 5, 5, 5. That looks correct. That should be all whites. And indeed, 5 was white in my palette. We've got blue, yellow, white, green, which is blue, yellow, white, green, which is what in the original image. And this is black, yellow, white, red. So this image has decoded correctly, which is amazing, absolutely amazing. And obviously we don't do anything with this at the moment. Oh. But we can hard code our... so we're already hard coding in this test data. What we'll do is I'll hard code in the drawing. Oh, yeah, there we go. So our canvas, we actually want to set the width to be 4. Right, it's 4. But we're going to set the style to be way bigger, so we get like a 100:1 zoom. Because this is only a 4 pixel by 4 pixel image, we just won't be able to see it. So we're gonna do a 100% zoom. It's gonna be amazing. Canvas. I need to turn off smoothing. Is that in context? Context. Image smoothing enable. There we go. Otherwise, it will try and anti-alias these 4 pixels over the 400 pixels that we're showing them, and it will look all fuzzy. And then because it's very small, I can do this without blowing everything up. So here I probably still do want to throw some sort of error. But I'm going to throw a happy error because it means we've drawn an image. And for a 4 pixel image, fine. We can use this horrible code. Image height, image width. Okay, cool. Those are probably consts. Yeah. Okay, for just trying to do whatever is easy. So let's just make this 4. Red, green, and blue. So here we're going to go through decoded. So this is decoded.length. And in fact, we can for of this one for pixel decoded. Let's see what we get. Now, this probably won't work because it never works in the first time, right? Yeah, there we go. Cannot read properties. Single iterator undefined. What is it? It's not defined. Oh, I never actually return. Never actually return from the function. There we go. We've got it out of the way, so now it can successfully work, and the universe won't be destroyed. Pixel is not defined. Oh, right, okay. I don't give it any sort of specifier or const. Error? Hooray. Let's see. Let's see. Partly amazing. Partly amazing. That image smoothing doesn't seem to have worked very well. And there's definitely something there. But it doesn't seem like what I was expecting. I can definitely say that. But I think this is a problem with our drawing code. Because these decoded pixels look spot on. So we're talking about pixel 0, global color table 02550. Oh, this is the global color table for our actual cat image. So the colors are all wrong. Okay. So that's good. Though white image smoothing enabled didn't work. I don't know. Maybe it's all prefixed in Chrome. It's sad if it is, but it wouldn't be the first time that I've been sad. So it's just that the colours we're getting are not correct. So I'm going to create a new colour table because I can. So we're just going to continue this testing, and we want black. So that's going to be 0, 0, 0. I have to put in the individual bytes here. Blue 0, 0, 5. Red. Yellow. And white. Not just one white, 3 whites. Still sad. I'm still sad. Still doesn't seem to be drawing correctly. Okay. So our first pixel is 100% green. Is that what we expected? Is that what we expected? I think I've deleted the... No. Our first pixel should be black. Are we looking in the wrong part of the table? Oh, order of operations, perhaps? Let's have a look here. What pixel times 3 is? It should be 0. Pixel times 3 plus 1 should be 1. No, it is 1. Okay, not that. Fill style is green. This is not the problem I expected to have at this stage. Oh, I'm an idiot. I'm an idiot, and I've covered up the chat. So it's possible. No, no one else. No one else got this. So okay, I'm just not using the colours. I'm just not using the right palette. Oops. Okay, so other than image smoothing being on, this now looks slightly better. Black, yellow, white, red, white, blue. I'm missing a blue, yellow, white, green. Why am I getting blue? Did I not include it in here? Blue is 1. That's what this is. So close. So, first pixel is black. Second pixel is yellow. So 3 is white. Red. Okay. We should just have a load of white. And get a blue. We do get a blue. X and Y wrong? Yeah, actually. Why is that on 4? Yeah, okay. I have an error. I'm drawing it off the wrong side of the screen. This should be because there is 0 indexed. So on every row except the first one, it will miss off the first pixel. So yeah, that is my test image, more or less. I'm annoyed about the image smoothing not working. But we'll do what we need to do. The decoding worked correctly. That's the important thing. The decoding worked correctly. So given that, let's just run the cat GIF through it and see what happens. So we've had a bit of a debug there. So this is going to be this global color table. We're just assuming that everything's in the global color table here, aren't we? We no longer do this because we already set the canvas size. Do we set the canvas size? Canvas width. Yep, we already set that somewhere else. We don't want to mess with the style this time. We don't actually need smoothing for this one. Hopefully this won't kill the CPU here. Let's see. Okay, it's not an unbridled success. Oh. Yeah. Image width. Image height. And I've actually just realized another bug, but it's just in the drawing code again. This one's to do with setting the color. So here where I set the fill style, Oh no, these are integers. These should be integers. It should all be correct. Oh, I'm not actually decoding any different data here. So these are image bytes. When test code goes wrong, oh, there's let's move this so I can see the window. Ah, no, that's whoa. If this dot next is 823, that means we've created entries for loads of stuff. We've created hundreds of new entries, and then our code comes in. It's only 476, and we're saying that is not in the dictionary. 476. Yeah, we skipped a load of stuff. So we're not actually setting last not equals null. So there is some route through here that means that setting the dictionary doesn't do anything, and it looks like it's probably going to be this. So I'm going to make a conditional breakpoint here. Last equals null. Now I want to know if we ever come through here again without anything. No. Interesting. So we do it once, and then never again. So every time through, we should be putting something in the dictionary, unless we are setting next to be way too high right near the beginning. How far through are we getting? Like, quite a long way to be stepping through that by hand, I guess. And next is going up. So next is going up, but the thing that we're putting in is undefined. We must be hitting this. We're doing this dot next plus plus. It's increasing the value. Oh, image rendering set pixelated. That's a new thing, relatively speaking, to me. It's possible that works, but I was sure that you could do it without that. I thought the image smoothing was all you needed. But we're past that now. So here we're doing this dictionary, this dot next plus plus, and so if we look here again, when we look in our dictionary, nothing is actually set for any of the values between 255 and 819. Or they've been removed somehow. They're being set to undefined, or this dot next is already starting out way too high. And I don't know which one it is. So, step through. So we get a clear code, fine. Then we get code 0, which is in our dictionary. So current equals just 0. Last is null. We set last to whatever the current thing is. We add it to our stream. Interesting. I wonder if that's where we're getting our form somehow. And the result adds a 0. Cool. Next code, 258, which is a new code. But that is the next thing. So we're not going to get an error here. So here we should get that current equals 2 zeros. The first part of the last one was a 0, and the whole of the last one was a 0, so it should be 0, 0. Current equals 2 zeros. Perfect. And then we set that into the dictionary with code 258 in that case. Let's go back to 259. And the last thing we had was 2 zeros. Stream is now another array. Oh, we don't actually use stream in array, do we? We just keep last, which may be an error. Result is now up to 3 whole zeros. I'm loading code 259. Another new code. So we're going to take the last thing we had, which was 2 zeros, and then the first part of that, which is another 0. 3 zeros, and we add to our result 3 zeros. We're now up to 6 whole zeros. So I guess I want to look through until we get to something that isn't a 0. So far, any unknown code must just be zeros all bunched together, because that's all we've put in. So we go through until we get to something that's not something that already exists. Oh, 265. That's going to be a bunch of zeros, isn't it? That is many zeros. Okay. Last is not null. It's 10 zeros. And current is 9 zeros, so we'll add those together. So we've got 19 zeros in a go. The next, in the next place in the dictionary. So the last item here, 19 zeros in a go. Amazing. So far, we've had nothing but code 193. We finally get something actually from our dictionary. One of the colours in our palette. I don't know what colour 193 is. I guess we could have a look. Stop. This. We'd have to stop out here, I guess. This dot global color table. So 0 is green. So a 0 index color that we've had a lot of times is green, and then we want what was our color? 193. We need 3 of them. So we've got that. Oh, can't read property 5. Oh, I'm looking to change the call stack position so that it's something that exists. Interesting. So that's kind of grey, a slightly reddy grey. Not very exciting. Not very exciting at all. So what else do we get? The next time we get something. So we've had a whole bunch of those now. 193s. Last is not null. This dot dictionary is up to 272 items. This dot next up to 273. We're getting a different color here. Yeah. So when we get our error, what is the last? What was the last good? The last good index in here it was 254. That's not true. We've had higher than that. Haven't we? So when we're coming through here, we're getting the dictionary has 275 items in it. And we keep going up, and those codes are getting higher and higher and higher. Dictionary has 300 odd items in it. And then at some point it goes back to, we get a clear code. We get a clear code. That's what's happening. We get a clear code, and then it all goes wrong. So we start off with one clear code, and we get another one later on. And at that point, we've reset the dictionary, and I think we have to set the initial, the code size back to initial. That would make a lot of sense. Okay. So how do we do that? Here method. So that means we actually need to store the initial code size. So that here we can say code size equals this initial code size. No. So we get a clear code, and after that, we reset the dictionary. Oh, I know what happens. So we reset the dictionary, and then we had these high numbers in the array. We're not resetting what next is. So this might not even be true. The important thing is that this has to be true. Okay, we're still getting the same error. I'm getting it at the same place though. So code is 476. Next is 261. So it's gone back down. It's a low number. Dictionary only goes up to 261. Now I'm just sort of guessing here. Maybe that's true. No. 476 would definitely receive code 476 when there are not that many things in the dictionary. Why? And I guess also, how come do we never get the, does our code size never go up? Yeah, so the code size never increases. The code size is always the same. So regardless of whether it's something we have to do or not, this can't be the problem. Technically, I don't need to do that there because it's in here. crazy and infuriating. What I'm going to do, just for now, is that when I get to that error condition, just next. Instead of throwing an error, I'm going to return result, so that we can see if the pixels we are getting are something approximately correct. Interesting. Doesn't really look right, does it? Oh. Well, after some limited success, where I managed to show the test GIF correctly, I'm now in a position where I am still getting junk. I'm still getting junk. I feel like we're so close. I feel like I just have a small bug now, and then we'll be showing that image. Why this looks kind of fuzzy again? This does seem to be zoomed. Canvas width and height are 480. Is that not what we're setting? Here? Image height and image width, are they not those values? Image width 480, image height 480, and it's just a canvas. It's 480, and its style is nothing different from that, right? It's 480 and 480. So why does it look kind of smushy? Technical term, smushy. This looks like the pixels are zoomed in. And this looks way bigger than 400 pixels, actually, 480 pixels. X. No, not that. I've got the zoom on. I've got 500 pixels, 500 zoom. So it's not worked, which is sad, but we're close. We're so close. I can smell it. I mean, yeah, it doesn't look like that, does it? And I'm not sure exactly what was supposed to be, what the issue is here. So that is, my 2 hours is up, and I don't really want to go over it. Now, my laptop that had the chat on has shut down because I didn't plug it into charge, because I'm that kind of prepared person. So bear with me a second. Now I'll get that. I will get that up. Code, so I can watch the video on my phone and see the chat here. Hopefully, with the chat, live chat. There we go. It's nicer looking junk. In fairness, almost looks like the wrong color, but in the right places. Yeah, I kind of agree, maybe. But we also know that we have a bug, that when we're getting to a point where we're reading the wrong code somewhere. And I'm not sure why, because there are things that didn't happen in the test image that obviously are happening here. I can't be 100% sure that my boundaries are correct. I can't be 100% sure that when I'm reading So where I'm deciding what to put in the dictionary, I may have misunderstood here. So I'm doing the last plus the current. I mean, is that correct? Or should it be like this, where it's just the first bit of the last one, instead of the whole of the current? So this line and this line are not referring to quite the same things by current and last. So this one I'm fairly happy with. This one I'm not, because we didn't use any of these in the test, as far as I'm aware. I'm not sure we used any dictionary item that wasn't created by this process. Could be wrong. Anyway, so you know what? I've got 2 minutes. I don't have to run off anywhere. So I will. No, I will. No, I will go away, and next time, damn it, I will have worked out what this problem is. I'm going to read through the spec and some samples, and I will get this cleared up, so that next time we can just do finishing touches. Once we're reading images, we will be able to. I will go through and make the drawing code more efficient, so that it doesn't kill the CPU whenever we try and do it. We'll write those color bytes straight into the graphics memory. We will work out how to do animation and everything else that we want to be able to do, so that we can show that GIF correctly. It is just now a case of decoding that image, the image data. It's the LZW decoding that is holding us back from showing that first frame. That I am sure of. Once we've got that, we will be in a great place. So, are there any other questions or comments before we go? Obviously, there's a slight lag between me asking that and you guys getting the option to actually type that in. So, oh, way back, like half an hour ago, Demetrius said let pixel. So that will be where we're drawing. You're like, well, shouldn't that be a let? Is that what you were suggesting? It can be const because it's const within each instance of the loop. So every time this comes through, this gets run again in a new context. Okay, it is a different pixel variable each time through the loop. And you can have that in a regular for loop. You could say, you know, for const I equals 0 or whatever. But when you get over here and you do I++, that doesn't work because you set it to the const and then you change it within the same context. But you could have this be like items dot pop, for example, and then that doesn't do anything, and I less than 10, whatever. So you can use a const in for because, yeah, as I say, it's a new context every time through. Though in this case, it's this would be okay. Actually, no, maybe not in this kind of for loop because this is initialization. This happens just once. These happen each time through. We don't know about the context. Ah, Jake and Paul would know this. This was one of their quiz questions ages ago. But certainly in the for of loop, new context every time. So if I put this as a let, nothing here is going to complain about it. A linter will actually pick that up and say, hey, actually, it doesn't change. It never gets reassigned. You could make that context. Keep forgetting where I have to go to look at the chat. Just a general overall question. How efficient fast do you expect to be able to make this? How efficient fast could I make it? I could make this almost native efficiency, about as fast as Chrome could do it. We could put the decoding on a separate thread in a worker. We could decode different frames in different workers. I'm not sure if we can parallelize the decoding itself because, because decoding each individual thing relies on the dictionary you've already built. You do have to do that in sequence. We can do this in WebAssembly and then run the WebAssembly module in a different thread. So that we could rewrite this in C and use WebAssembly to do it. We could use WebGL to do the actual rendering rather than dealing with the pixel data itself. Could we use WebGL to do the decoding? Maybe. No, you can't carry on state. So we could pass in the codes, so the result that we get through this thing, the image bytes, and we can pass through the color table as information to a WebGL shader, and then the WebGL shader does this bit, working out what the colors are. That would be a slight improvement. So we could make it pretty efficient. There are lots of things we could do. How far will I go? Probably not that far. I have no intention of doing WebGL here or WebAssembly. At the places where I'm being inefficient, so where I'm doing all these concats of arrays, that just means that I would use array buffers and manage it a bit more carefully. Actually allocating allocate a large array buffer, for example, fill it up in pieces. I don't know what of that will do. The drawing, you can get at the actual bytes of the canvas. So you get what's called an image data object. And that has RGB and A, so red, green, blue, and alpha channels. And it's just 4 bytes per pixel. It's just a uint8 array, and you just set all the bytes. So we'd basically be copying over these bytes into there. And that's way more efficient than this thing, where I'm calculating this fill style based on the CSS name, on the CSS RGB property. This is just mad, because I'm doing it for every pixel. 480 by 480. It's not absolutely enormous, but 480 by 480. 230,000. So, we're running this 230,000 times for that cat GIF, or will be. Which is a lot to be doing. So we manipulate this, we process the string, the backtick string, and then the CSS processor goes away and turns that into a color, which gets set to fill style. And then we fill a rectangle, a 1x1 rectangle for each pixel, which has an overhead because the code will be written to assume that your rectangle is not 1x1, almost certainly. I don't know, maybe there's a fast path. Okay, I guess you could split decoding by the clear code to parallelize. I'm going to say No. I mean, I get where you're coming from. So when you get the clear code, you reset the state, and so magic. You can split there. That's true, but the problem is that you can't work out where the clear codes come in the stream without reading the stream to find out what you get. You'd have to go through the stream and do almost all of this to work out where the clear codes come in. You would have to do everything except you wouldn't have to update the dictionary, and you wouldn't have to return a result. But you'd have to, I guess you'd have to do this, and you'd have to look for the clear code. You have to do this. Okay, it would be more efficient than processing it completely, but I'm not sure how much you then gain, because we're already going through. We have to go through the whole stream to look for where those clear codes come in the stream. Because you've got to remember that as the code size grows, the clear code, the encoding of the clear code value itself will be the same. But let's say we start out with 2-bit codes, so our clear code is going to be the smallest 3-bit, the smallest 3-bit number, which would be 4. So anytime we see a 4 in the stream, that is the clear code, but we don't know how many bits. That table could grow very quickly so that we're reading 8 bits at a time, and then our clear code would be a 4 written in 8 bits, whereas early on it would have been a 4 written in only 3 bits. Does that make sense? Yeah, you have to parse the entire stream to find out where the clear codes are. Cool. Thanks for watching, anyone who was watching. Thanks for chatting. It was good to see things in the chat. It makes it feel slightly less like I'm just talking to myself. That is very useful. Yeah, thanks again for coming. Hopefully next week we'll be more wrapping up here. But yeah, catch you. Take care.